Good morning, Astronomy 1010. It's week 11 or something like that. Today, we're going to cover planetary atmospheres. Last class, we tied up terrestrial geology with a bow. You learned little details about the four geological processes. You learned a little bit about the types of geology we find on the different terrestrial planets. But to fully understand how terrestrial geology works, we have to include the atmosphere component. So you guys know your terrestrial planets, presumably. Which ones have atmospheres?
Earth, Venus. I know at
Mars
one point
does.
Mars did have an atmosphere. I'm not sure if it still does.
It still does. It's thin, but it is substantial, right? Remember when that Perseverance rover landed recently on Mars, they deployed a parachute to aerobrake the velocity of the spacecraft in its atmosphere. I don't know if you guys were there that day. Did we watch that together? I watched it with one of my groups. I thought it was you guys.
It was us.
I always spell Perseverance wrong. Perseverance landing. Remember, they deployed that really cool parachute to land in the atmosphere. I was wondering if we had any live images from there. I have several images today in which you can see the atmosphere of Mars. I was hoping we could see a picture of the parachute. The parachute design was actually pretty cool. There's some cool binary message encoded in this thing. Another thing that Mars is famous for, and this is pretty wild, Mars oftentimes has blue sunsets, unlike Earth. So the picture from, I believe, the Curiosity rover, oops, sorry, let me try this again. Blue sunset on Mars. One of the most iconic images today that we have from Mars is, and this makes for a really cool wallpaper if you just want to look at some cool planetary science stuff. Yeah, here's a picture of the blue sunset on Mars. Something about the way the dust grains, I believe they forward scatter blue photons. I can't remember how the scattering works here. That's something I should remind myself about. But this legendary picture of a blue sunset on Mars. So Mars definitely has a substantial enough atmosphere to create cool sunset effects. You can see Mars's atmosphere from Earth through a telescope. It's thinner than Earth's, but it's there. So this is, I think I have this in my slideshow today. But here's a picture where you can actually see the atmospheric limb here. Mercury does not have a substantial atmosphere. People study sodium atoms bouncing around the surface of Mercury. That's not a real atmosphere. Let's get real, okay? The moon is almost completely airless. So we're now going to restrict our domain to studying just 3 planets. And in a way, the study of terrestrial atmospheres is a little bit like Goldilocks and the 3 atmospheres, okay? This one is too thin, this one's too thick, and Earth's, of course, is just right. So you can see I started my slideshow here, showing a picture of Mars's atmosphere. You can see Earth's atmosphere here. And I haven't shown you guys too many pictures of Venus yet, but eventually I need to get around to that. Remember that Venus's atmosphere is made of mostly carbon dioxide, but seen in true color from space, it looks something like this. It's whitish with sort of yellow clouds. You can see some sort of bands. In the higher altitudes, Venus's atmosphere has very, very high speed winds. But as you get closer and closer to the surface, all the wind stops and the planet's atmosphere becomes very, very stagnant. So stagnant, in fact, that Venus suffers from what we call a runaway greenhouse effect. And, you know, on Earth, if you go to the equator, temperature conditions are much different than if you go to the Arctic Circle. On Venus, this is not the case. Venus's global temperature is the same everywhere you go on the planet. That's how intense not just the greenhouse effect, but you learned today that's about convection in its atmosphere. It works differently than Earth's. So we got a whole bunch of stuff to learn about today. Of course, in these kind of situations, you have to sort of start off with some basic stats. What are these atmospheres made of? And these are some notes we're about to take over here on the board. So Earth, oh, sorry. I don't know why I listed all of these planets. Now that I think about it, I would actually just like to compare all three. Is this my most recent slideshow? This does not feel... Okay. Something's going on here. I have a more recent slideshow. That one's not as up to date as I would like. And I had this issue last class too. I thought this would be the most up-to-date one. Just bear with me a sec here. Because over the years, I've added a few deets here and there that are worth sharing. Okay, there we go. This is the slide I was looking for. Function F5.3. So what we want to do is we want to ignore Mercury and the Moon. Let me just mute. Oh, hi, Kim. Okay. What we want to do is we want to focus on these guys here. Sorry, I had to wiggle around all the little doodads on my screen so I wouldn't block them. I want you guys to notice a few things. I should probably start taking notes. The atmospheres of Venus and the atmospheres of Mars are basically identical. It's Earth that's a little bit of a weirdo. And what we're going to really want to pay attention to is carbon dioxide. Remember that well, actually, let's see what you remember. Where do the atmospheres of the terrestrial planets come from? How do terrestrial planets gain their atmospheres? This is a point I've already covered. If you can remember.
One of the main theories of how planets got their atmosphere was through volcanism?
Yep, and Ryan's chimed in on that as well in the chat. Exactly. Where there are atmospheres, there are almost always volcanoes. Okay, so and do you guys remember when I showed you the pictures of the terrestrial planets as layered by density? Although the surface ages of the planets are quite different, remind yourself that the composition of the planets themselves are remarkably the same. They are layers, and this is the picture where I attempted to show that, slide 28. Oh, come on. Sorry. Slide 28. Composition-wise, Earth, Venus, and Mars are basically the same. It's layers of silicate rock with a mantle, and then in their cores, a nugget of iron and nickel. And the point I'm trying to make is volcanoes on Mars, volcanoes on Venus, and volcanoes on Earth are basically spitting out the same gases. Can you guys remind yourself what some of those volcanic gases were? Obviously, carbon dioxide is going to be a principal one. What are some others?
Also water, diatomic nitrogen,
Yep.
and sulfur dioxide.
Yeah. So all of these gases, with the exception of sulfur dioxide, which I think tends to crystallize into a salt, we're seeing these gases in the atmospheres of the planets. So let's take some notes. Planetary atmospheres. The idea is that I want you guys to memorize the compositions of the atmospheres, or at least have a vague idea what they are. Before we get too deep into this lecture, a couple of weeks from now, it's going to be time for the final exam. I don't know if I've talked to you guys about this, but I am open, if you guys are open to it, to potentially letting you use your midterm grade exam in place of your final as a means of getting out of taking that awful test, which is probably going to be wicked stressful, right? Is that the kind of thing you guys would be interested in?
100%, yeah.
Yeah. Kim, Jenna, you all like that idea? All right. I want to say for the record, especially for the benefit of people who watch the videos later, I do have a final exam made, and it is your right to take the final if you want to. If there's anyone out there who does want to take the final, then you should probably get in touch with me and let me know that you're interested in that so that I can make plans. Otherwise, if most people would rather just spend the rest of the class learning some cool stuff, doing a couple of homeworks, and then maybe, you know, letting ourselves off the hook a little bit, that's something I'm open to doing, okay? My take on it is you guys already worked hard on that midterm. If I can let you out of some stress at the end of what is probably a stressful semester, if I can free up some time in your lives, that can really help you to get your other classwork done and stuff. So let's talk about that next week some more, okay? Okay, so in theory, if you were to take a final, then you would be responsible to memorize the atmospheric compositions. Venus, Earth, and Mars. So 96% of Venus's atmosphere, and I believe it's 95% of Mars's atmosphere, but let's make sure that I've remembered this correct. 95 or 96% of Mars is about the same thing. Yeah, okay. So I wasn't crazy there. So 95% of Mars and 96% of Venus is CO2. Earth's primary constituent gas, 77%, is diatomic nitrogen. While diatomic nitrogen, as Jenna points out, is also a volcanic outgassing component, it's a little bit weird that if the Earth has the same chemical composition as Mars writ large, and by the way, when you sample gases from Earth's volcanoes, they're pumping out CO2 too, in roughly the same mixtures. So it's not like Earth isn't pumping CO2 out of its volcanoes. It's just that CO2 doesn't stay in the atmosphere. There's a mystery. There's a reason why. Does anyone know where Earth's carbon dioxide ends up? I just wonder if anyone knows.
This is just a guess. Does it have anything to do with plants and plant life? Because we have life
Actually,
and we don't.
Plants, algae, cyanobacteria only contribute a very small amount to the carbon dioxide budget of Earth. It's not plants, although plants do, you know, absorb CO2 and expirate some oxygen. They are responsible for Earth's oxygen component. Earth, of course, has 21% diatomic oxygen, and that's a bit weird, right? Oxygen is a violent gas. It's not a gas that's pumped out in volcanism. That has something to do with not so much plants, Ian, but cyanobacteria, the blue-green algae that makes up oceans and waterways. Okay. The next biggest component of Mars and Venus, diatomic nitrogen. There's a gas that we see in all three planets. It makes a small percentage of the gas that's released in volcanoes, and it's argon, okay? Argon is a noble gas. Maybe, you know, this is maybe a small amount. For Venus, the 0.5% is other stuff. It's a complicated mixture of things, but argon is probably part of that. For Earth, 1% is argon. 2% of Mars is argon. If you ever took a chemistry class, let's take a little peeksy-weeksy at the periodic table of the elements. This is just for those kids who either didn't take chemistry or didn't learn anything when they did take chemistry. If we can just grab ourselves a periodic table of the elements. It might be nice to have the Sergeant Welsh one around. Is this the 2000 pixel one? Yeah. You guys know I love my Sergeant Welsh periodic table. All of the elements in the final row of the periodic table, sorry, the final column. Wow, I'm not making a lot of sense here. These are called noble gases. The deal with the noble gases, does anyone know what the deal is with these things? Helium, neon, argon, krypton, xenon. These atoms, like all other atoms, have equal numbers of protons and electrons. But the number of electrons in this final column is such that they perfectly fill up all of the orbital shells that an atom needs to become very stable. This makes these elements chemically inert. Helium will only appear in a gaseous form because it will not form compounds and molecules and salts and crystals. They have no desire to bond or pair with any atom or molecule. They're just perfectly happy being gases and floating around by themselves. And not. This is one of the reasons why you can inhale a small amount of helium and talk like a clown, because the gas is not going to easily dissolve into your bloodstream or affect you very much. It just changes the pitch of your voice for a little bit, and then you inhale it. You of course still need your oxygen, but you can actually replace nitrogen with helium, and you can breathe, and as long as you have enough oxygen in there, it's fine. Helium is lower in mass than neon and argon. So although there is a lot of helium in the protosolar nebula, planets like Earth and Venus and Mars could never have enough gravity to hold on to it. The helium just boils away. I don't know why neon gets skipped and why we find more argon, but I suspect it's for a similar reason. Argon is just a bit more massive, so it just kind of gets mixed up in the compositions of the planets, and little bits come out during volcanic outgassing. So the fact that argon is rather heavy is probably one of the reasons why we find it in the terrestrial planets. Earth and Venus behave very different. They look very different in terms of their atmospheres. Here's a cool statistic that I learned, something that I found interesting. If you could travel to Venus, so remember, Venus has a thick atmosphere. Its atmosphere is hundreds of times the pressure of our own. You couldn't even stand up in your spacesuit on Venus because the pressure of the gas would just crush you like a can. It's very intense. Earth has a medium atmosphere, and Mars has a thin atmosphere. Here's a cool statistic that I learned. If you could take a vacuum cleaner, a planetary-sized vacuum cleaner, and just suck up all of the carbon dioxide on Venus, its remaining 3.5% diatomic nitrogen would be equal in mass and volume to the 77% nitrogen of Earth. Isn't that insane? Basically, these two quantities of gas, they look different because they're percentages of different atmospheres, but they are identical in volume, these gases. So basically, Venus has Earth's atmosphere there, and all of that is dumped on top of Earth's atmosphere. That's how much thicker Venus' atmosphere. And it does suggest, okay, remember that Venus and Earth are sister planets. They both have radii of a little over 6,000 kilometers. So that actually makes sense because they should have similar amounts of volcanism. Their atmospheres are a similar percentage of the planet. Why did Venus pump out so much CO2 and Earth didn't? Obviously, Earth had to be pumping out the same amount of CO2, but something happened to it. That's something we have to talk about today. Another planetary mystery, which I already kind of spoiled the surprise. Diatomic oxygen does not appear on any of the other planets. And it turns out that this is created by life itself. So life is responsible for the generation of Earth's diatomic oxygen. That's a cool thing to think about because most of the time people assume that life exists on Earth because there's oxygen for it to breathe. In fact, it's the other way around. Life got started on Earth before the oxygen, and life has terraformed the planet over billions of years to create conditions more suitable for life, which is kind of wild. Terraforming is something that happens on Earth already, thanks to our friends, the blue-green algae.
Yeah, the plants really helped us, except for that one time they caused the oxygen holocaust. But
Yeah, if you look at the, it's cool to look at a graph. I wonder if it'd be easy to find the history of Earth's oxygen. If you look at a graph showing us the percentage of oxygen in our atmosphere over time, it's pretty wild, right? So I think this might be what you're referring to here. If you were to go back a billion years ago, oxygen makes up less than 5% of our atmospheric gas. And as life gets more of a foothold and cyanobacteria populate oceans, rivers, and streams, we can see the oxygen growing. I can't remember. Do you remember, Ian, what caused the switchback? This is something I should know about, but
I don't remember all the specifics, but I do know it was one of the 5 mass extinction events we've had. Was that plant life and photosynthesizing life got so out of control that it filled our atmosphere with so much oxygen that it
well,
caused,
so much means 35% according to this graph,
so
right?
much
Yeah.
more than was stable for life, and it caused mass extinction.
Very interesting. Today it's hovering around 21%, and since organisms on Earth evolve over these kinds of timescales as well, the organisms that are on Earth today have adapted themselves to that 21% oxygen. I want to talk about trace atmospheric gases on Earth, because these trace atmospheric gases sometimes have a very large effect on the planet itself. And in the case of Earth, two that really scream out for attention are the percentage of Earth's water, or the percentage of Earth's atmosphere that's comprised of water and CO2. And the numbers are kind of easy to remember. It's 0.4%, 0.4%, and 0.04%. So let's add those kind of in parentheses, okay? So 0.4% is H2O. And weirdly, CO2, which actually still has a profound effect on the temperature on Earth, only makes up 0.04%. I want to make a big point about atmospheres, and I'd like to have you meditate on a picture of Earth's atmosphere with me. So let's go let's go to the internet and let's just call up a picture of Earth, okay? So let's say that you were an alien from another solar system, and you traveled to our solar system for the first time and thought, whoa, check out this planet. This planet looks like it's kind of cool. Maybe there's some living organisms there. If you looked down at the atmosphere of Earth with your eyeballs, what would you conclude is the primary atmospheric gas in Earth's atmosphere?
Water?
That's right. Because the first thing you see, Jenna, are all those big white watery clouds. And it looks like it's a pretty substantial fraction of our atmosphere. And yet, Jenna, what percentage does water actually make of our atmosphere? 0.4%. This is an important takeaway, not only for Earth, but almost every planet in our solar system that has an atmosphere. What you see is not what you get. Small trace compounds in an atmosphere are often responsible for all of its visual appearance. Let's talk about CO2 for a second. Do you guys know what CO2 is? Tell me about CO2. Where might you have encountered this in your everyday lives? What about dry ice? Ever make yourself some dry ice cream or something like that? Carbon dioxide, 1 atom of carbon, 2 of oxygen, is the composition of dry ice. And in a vaporous form, it's either whitish when it's condensed, or more often CO2 is just clear and transparent. The atmosphere of Venus is 96% CO2, but all of those yellowy clouds that you see, there are trace elements in the clouds that are responsible for that composition. By the way, one of the interesting components of Venus's atmosphere, although it makes up a very tiny percentage, Venus has a very caustic acid rain, which is capable of melting spacecrafts. These drops of acid rain come down on the planet. And that's one of the things that we saw dissolving that spacecraft when I showed you those pictures of Venus. So there are acid rain clouds. I'm talking about like that acid that melts metal, like you saw in the movie Aliens, right? It's some pretty harsh, caustic stuff. And I did show you guys those pictures of Venus last class, right? Where you could see the sort of the flat volcanic rocks. Okay, cool. Well, if you're going to learn about planetary atmospheres, if we're going to figure out what happened to the carbon dioxide and how they function, we're going to have to revisit an old pal of ours, the ideal gas law. Y'all remember the ideal gas law or what? I would really love to be able to show you guys a flash file. In fact, I'm going to do one thing for a second so I don't bore the video watchers later. I'm going to temporarily pause. We have activated my little dorky flash file. I'm afraid that the buildup was probably not what's actually happening here. Okay, but we did it. Thank you, Ian and Kim and friends, for either helping or tolerating me while I figured that out. All right, so this is a happy moment. I finally have access to my little, I have a whole bunch of different physics simulations, and this is one that I like. All right, so here we go. We got a box. We're going to learn about the ideal gas law. Let's pump it up. Pump, pump. Okay, here we go. So here are some gas particles, and you can see that the particles are all moving around with a distribution of velocities. Some are moving fast, some are moving slow, some are moving somewhere in the middle. They're all kind of crashing around into each other, and they have a number of state properties, properties which define the gas. The pressure, the temperature, and the density of particles. And these things are related by the ideal gas law. Now, I'm going to do some things to this in a second, but I want you guys to review this with me on the board. Does everyone have this stuff? All right. Do you guys remember the formula for the ideal gas law? You would have learned it during the chapter on the sun.
Is it P equals little n times K times T?
Very good. And so this is the ideal gas law. Pressure equals number density times the Boltzmann constant times the temperature. All right, let's review each and every one of these things in our notes. P is the pressure. Do you guys remember the units of pressure?
Pascal?
Very good. PA is the abbreviation for Pascal. Remember that 1 atmospheric pressure, the atmosphere of Earth is 100,000 Pascal. Okay? That's just a kind of useful number to have in the back of your head as a reference. N tells you how many particles are in a cube roughly the size of 1 dice. It's known as the number density. The number density is measured in particles per cubic meter or particles per cubic centimeter. You'll see both appear in our equations today. Sometimes just written as 1 over m cubed. Sometimes even written as m to the minus 3. That's the number of atoms in a box. K is the so-called Boltzmann constant. This will appear in several of our new equations that you'll learn in this chapter, and I kind of have to get to them kind of quickly. This number always shows up when you're working with gas particles. It's known as the Boltzmann constant. There's a lot of physics packed into it that you don't need to worry about at your stage. Just know that it just pops up in all kinds of different equations involving gases. And finally, T, of course, is the temperature. Temperature will be measured in Kelvin, of course. The ideal gas law tells us how these things change when we modify the gas in some way. Notice that the temperature of this gas is 300 Kelvin. As a reference point, room temperature is 293 Kelvin or something like that. So this is pretty close to room temperature. Notice that the atmospheric pressure is little over 1 atmosphere. So similar to the gas in this room. What's going to happen if I add a little bit of fire? What will happen to those gas particles?
They're going to speed up.
That's right. And here you can see me jacking up the temperature. And sure enough, the kinetic energies of the gas particles go up. We can add some ice and we can cool it back down. You'll see them slowing down. I want to show you something else here. What if I take Mr. Robot and I squeeze the gas? What's going to happen then?
It speeds up.
Yeah. This is how the pistons in your car work, right? Well, they kind of work in the opposite way. You explode the gas and they push the piston out. Notice when I open the box back up, pressure drops a bit, but the temperature stays the same. Okay, let's try this. Let's cool the gas down. Over here on the right, and I want you to pay attention to this, there's a button for gravity. What do you think will happen to the gas when I add gravity? Let's find out. I want you to watch. Watch the temperature, watch the pressure. Wa-boom. What did you see have? The temperature went crazy, right? Gravity is like squeezing gas particles. In fact, the difference between a planetary atmosphere, of course, and gas in a box is that there is no box around a planet, right? Gravity is the box. And if you travel from the sea level of a planet up towards outer space, the gas particles will decrease both in density and their temperatures and their pressures will change. And this is the key idea behind understanding how planetary atmospheres work. I want you guys to play a little game with me. Can I erase this for a moment? I want you to imagine a hot air balloon in which we travel from Rhode Island's sea level up into outer space. And let's imagine, I think the first time I do this is going to be, hold on, I don't want to share just yet because I'm trying to keep a little suspense and a little surprise here. So bear with me, students. The first one is going to be the density. Okay. So let's imagine I make a little graph called the density scale height. And in this little cartoon graph, I'm going to plot the height that we travel in Earth's atmosphere. Somewhere up here will be outer space. How far do you think you have to go? How many kilometers up do you have to go? What was, oh, T was temperature in Kelvin. That's right. How high up do you have to go before you're in outer space?
6,400 kilometers.
No, that's a full Earth radius. By one Earth radius up, you are totally, so I'm talking about from the surface of Earth. So this is the ground, okay? You probably don't remember the height of the International Space Station, but it's about 400 kilometers up. So maybe we could take, by the way, do you know the ISS every year has to make a periodic thrust correction because small trace amounts of atmospheric gas add drag and decrease the height of the satellite? However, if you've ever seen a picture of the ISS, and I know you have, you're pretty much in outer space at that point, right? So maybe 400 kilometers up would be considered outer space. How tall is Mount Everest? Anyone know? Tallest mountain in the world?
I know at one point it's somewhere, I mean, this might be completely wrong, somewhere around like 10 miles, right? Or
like
something.
it's like 8 or 9 kilometers, I think. 9 kilometers.
Okay. I didn't know kilometers, but
yeah, I don't know miles.
well, there you go.
All right, so between the two of us, we're pretty much useless. Okay, so maybe somewhere up here, like 10 kilometers. I think 10 kilometers is pretty much airplane height, and it's similar to Mount Everest, okay? the density of air in this room, if I made a three-dimensional box, 1 meter cubed, and by the way, remember that my dry erase board here is roughly a meter across and roughly a meter tall. So imagine a cube that's about the size of this dry erase board. It'd be like half a refrigerator box, okay? The density of air in kilograms per cubic meter is like 1.2 kilograms per cubic meter at sea level. So if I were to measure, now here I'm not going to measure number density because I don't have the slide for it, but I have density in kilograms per cubic meter. And at the ground level, it's 1.2, all right? What do you suppose the density of air is at the International Space Station? Approximately.
Very close to 0, I would assume.
That's what I would assume too, right? There's no gas part, not many gas particles up there. If I take a hot air balloon and ride it from the ground all the way up into outer space, I have to go from this data point. And by the way, think about it. The air sitting over the top of your head is roughly has the same mass as this 1 kilogram weight. We tend to think of air as being weightless or massless, but it's not. And that pressure on top of your head feels normal. I've got to get from this point to this point, and I can think of 3 different ways to do it. Way 1 would be a linear drop-off, meaning for each kilometer in Earth's altitude that you travel, you lose a proportional amount of gas particles. So this is a linear drop-off. A second option would be an exponential drop-off. That's where you start to kind of lose a lot at first, but then you asymptote out to 0 as you get to outer space. We call this in mathematics an exponential drop-off. The only other way I could imagine besides linear or exponential is what we call logarithmic. In a logarithmic drop-off, you don't lose much at first, and then you asymptote out the other way. Now, there's no reason you guys should know which is the correct graph. But if we were scientists, if we were playing scientist, one would hypothesize one of these as the most likely outcome to kind of test your intuition. And then you'd actually send up your hot air balloon, your weather balloon, and you'd measure it. So you guys take a guess. What do you think will be the correct way that air drops off as we get towards outer space?
Exponential?
And we send up our hot air balloon. We take our measurements. Function of 5, 10. Boom. And yes, Ian, your science intuition is good. Ian, by the time I reach airplane height of 10 kilometers, by what fraction has the density of air decreased? No, look, just read it off the graph. 1.2 versus 0.4. You can divide those two.
12
divided by 4. 12 divided by 4.
Oh, really? Okay.
Right?
That would
1.2,
be
0.4.
1/3.
Yeah. So we've lost maybe 2/3 of our gas, and the density of air is 1/3 what it used to be at sea level, correct? How about by the time I get to double airplane height? 12 divided by
That would be 1/12, right?
1/12, right. And then it quickly just tapers off to absolutely nothing, right? And this graph only goes up to about 90 or 100 kilometers. So this is one of the reasons why we have to pressurize. Well, we'll talk about the pressure next. Do you think it will look the same or different if we measure pressure instead of density?
I would think it's probably similar.
And sure enough, you are correct. The pressure of atmospheric gas drops in a similar exponential fashion. Ian, by the time I get to airplane height, let's call that 20, by what fraction has the pressure of the gas dropped?
1/5.
Yeah, 10 over 2 is 5. So yeah, we've basically got to 1/5 the pressure. This is why you have to pressurize your airplane cabin, right? Remember that humans are remarkably intolerant to changes in pressure. We find that very, very distressing. What do you think is going to happen to the temperature?
The temperature is gonna drop, I would assume.
Should it be exponential?
I think so. I mean,
All right.
because I guess if we're looking at the ideal gas law, they're all kind of fitting into the same thing. So
Students, prepare your asses to learn. In fact, it's fucking insane. The temperature drops, then it rises, then it drops. And by the way, if you could keep going this graph, it actually goes back up again. It's totally bonkers. Understanding this graph, the so-called temperature scale height, is the essence of learning about atmospheric science. It's a key graph. And in fact, it's a place where your book really, really exceeds itself in making a very beautiful information graphic. So here's one from a graduate textbook. It's going to turn out that the temperature makes a bunch of radical switchbacks, and we actually define different layers of Earth's atmosphere based on this. Let's look at a nice cartoon picture that your book has that I love very much. This information graphic explains so much. We can see that the temperature at ground level, the average temperature of Earth is around 15 degrees Celsius or so. And that's an average between equator and poles. As we get up to Mount Everest or airplane height, we see it drop down to about negative 60 or so. Then we enter this layer that you live under is called the troposphere. All right, that's where most of Earth's atmospheric gas is located. Then the temperature begins to rise in a key level of Earth's atmosphere known as the stratosphere. It goes back up to about negative 10 degrees Celsius. This little temperature rise is known as a stratospheric bump. There's a lot of science going on in here. Then it drops back down up towards the thermosphere. And notice as you get closer and closer to the vacuum of space in the exosphere, the temperature just keeps going up forever. Now let's think about that. The number of particles is dropping and dropping and dropping, but those particles that remain are traveling faster and faster and faster. Why is that? First thing we got to do, oh yeah, go ahead, Ian.
My guess would be that they're the first to make contact with sunlight. So they absorb.
Remember, sunlight, the sun is a black body emitter, right? When you're thinking of sunlight, Ian, you're thinking of being on the ground and you're thinking of visible light only. I'm not saying you're wrong. I'm saying that sunlight is more than just visible light. It's infrared, it's visible, it's ultraviolet, and it's X-rays. But it actually turns out to not be sunlight so much at that altitude. It's the solar wind that's really kicking up those gas particles. You all remember what the solar wind is, right? Someone tell me about the solar wind. No, nothing? Okay, we'll talk about the solar winds in a second. Let's reproduce that graph because it's kind of important. This graph, which is the essence of atmospheric science, is known as the temperature scale height diagram. And you kind of have to know about this if you want to know anything about atmospheres. We'll start off 15 degrees Celsius. We'll try to reproduce it. And up to 10 kilometers, it's going to drop down to about negative 60 degrees Celsius or so. So sure enough, in the troposphere, the temperature drops. Then it turns around, and I think it peaks around 50 kilometers. Let's just check that again. So you can see somewhere around 50 kilometers, we get the temperature rising again to make the stratospheric bump, and then it drops to 80, okay? So this graph won't make a ton of sense, but in terms of its scale, we'll go back up, we'll come back down, and then we'll keep going up forever. These switchbacks are going to help us define layers of Earth's atmosphere, which I expect you to know. The bottom layer, where you live, where temperature drops, that's called the troposphere. The second layer, where temperature rises and falls again, is called the stratosphere. The stratosphere turns out to be a very interesting layer of Earth's atmosphere because it's a layer of Earth's atmosphere in which high temperature gas sits on top of low temperature gas. And that's not a normal scenario. The air in your room circulates usually with warm air rising from the bottom and cool air being displaced on top. Little convection cells even take place in a classroom. When warm air sits on top of cooler air, the atmosphere becomes very stagnant and no convection can mix the air up. This stagnant layer of Earth's atmosphere has a lot of important science going on in it. And in addition to this layer being called the stratosphere, this little feature here is a feature that planetary scientists refer to as the stratospheric bump. And in some ways, it's considered an indication that living organisms exist on the planet. There's a layer where the gases become heated and ionized. That's the thermosphere. And the very last wispy, tenuous layer, and this layer is the only layer in which gas particles are constantly boiling away into space. That layer of any planet's atmosphere is known as the exosphere. And we are going to adopt similar terms for the other planets as well, even the gas giants, which are essentially all atmosphere. Ian sort of put his finger there on the pulse of what was going on. These changes in the temperature of Earth's atmosphere have to do with interactions between light from the sun and the Earth, but it's a little more complicated and nuanced. In fact, Ian, one of the reasons why I love this information graphic from your book is they kind of explain the whole damn thing in one shot. The troposphere, for instance, Ian, is not being heated so much directly by sunlight as it's being heated by Earth light, okay? So check out what's happening here. Visible light from the sun is transparent. Our atmosphere is transparent to visible light. The visible light travels to the ground where it heats up the ground rock. Earth then becomes warm, and the warm rock begins to glow with infrared light. Infrared light provides the heating through greenhouse gases that warm up the troposphere. Why is the temperature dropping in the troposphere? Because you're getting further and further away from the light, which is not sunlight, it's infrared Earth light coming from below. At some point, the temperature begins to rise because you get to a layer of our atmosphere where ultraviolet light has penetrated down this deep. And normally the UV light would actually make it all the way to the ground if it wasn't for a key atmospheric element, a very trace element called ozone. Ozone, or O3, is a diatomic molecule, and it's super, super good at absorbing ultraviolet light. So we can make a note that the stratosphere is being heated up by ultraviolet photons plus O3, or ozone. Ozone acts like a kind of living shield that blocks ultraviolet photons. And let's draw a little picture down here of the interaction. If you're wondering where ozone comes from, it can either come from ultraviolet photons or X-rays originally breaking up diatomic oxygen, but oftentimes this ozone molecule is created during lightning storms, okay? And ozone is responsible for that kind of fresh, clean smell that you might smell outside after a thunderstorm. Ozone is also a poisonous gas, and it will kill you in sufficient concentrations. Okay, so it's called ozone, O3. Especially good at blocking ultraviolet photons. So here comes a UV photon from the sun. Remember, ultraviolet is shorter wavelength and higher energy than visible light. When it hits the ozone, it busts it apart. We call that photodissociation. And the three oxygen atoms break apart. They now have high kinetic energies. And the ozone, with their new high kinetic energies, they go mosh pitting around with the other atmospheric gases. As they slam into nitrogen and slam into oxygen, the temperature rises, okay? But what's so cool about ozone is after they bop around and lose kinetic energy through collisions, the three oxygens come back together and they reform. So it's kind of like a living bulletproof vest that can regenerate and reheal itself, because after they lose their kinetic energy, boom, they reform the ozone and they're ready to absorb another ultraviolet photon. Now, Ian or anyone else who thinks they've got the right intuition, explain to me what's going on. In this portion of the stratosphere, why do I see the temperature getting higher and higher up to 50 kilometers? Remember, this layer is caused by interactions between ultraviolet light and ozone molecules. So-
I mean, I guess because the ozone is dense enough that it kind of sits in the middle there. So there's a higher concentration.
The lack of stratosphere means ozone cannot easily drift to other layers of the atmosphere. But I was just looking for a simple answer of why it's hotter here and cooler there. Let's say I try it in the bottom layer. I tried to explain this to you a moment ago. Why is it warmer here and cooler there?
Well, because of the infrared light coming off of Earth.
So what about it? Why does the temperature drop?
Because you're getting further away from that heat
You're
source.
getting further away from the light source. So by analogy, Ian, why do you think you're getting warmer from here to here?
You get closer
Closer to what?
to a heat or a light source.
You're getting closer to the light source, right? So as you're getting close, like more ultraviolet photons are penetrating here, so you're getting closer to the light from the sun, then why would it switch, Jenna, and start to drop again?
Because you're, oh, I was going to guess because you're getting further from it now.
Further from what? You're getting closer to the sun if you go from here to here.
From the grounds.
So why does that matter? What's happening as we go from here to here that causes less heating?
That was the part that was confusing me, because that's why I didn't immediately go to.
Oh, because you knew I was going to ask that question next.
Yeah.
You didn't want to get, all right. I wanted to see if you guys could think your way through this. It's a two-part factor, right? Here we're getting warmer and warmer because you're getting closer to the light source. But remember those other two graphs where I showed you the density of particles and the pressure of particles dropping? As you get higher and higher up, there are fewer air particles and therefore fewer ozone shields to block the ultraviolet. So it's kind of like a calculus problem where then it starts to drop again because you're getting fewer and fewer ozone particles up here to absorb the ultraviolet. The two kind of hit a maximum right here at your stratospheric bump. That's where you get good exposure to the ultraviolet light, but there's enough dense enough group of particles to absorb the ultraviolet photons. If you think about it, this suggests that without oxygen in our atmosphere, that there would be no ozone, then we would have no stratosphere. Can you guys imagine what Earth would be like if we didn't have a layer of our atmosphere to block ultraviolet photons? Where would those ultraviolet photons end up?
On the surface?
Yeah, and you know what happens when ultraviolet heats up your skin when you go to the beach, right?
Yeah, sunburns
And that's from the trace amounts of UV that actually make it to the ground. Could you imagine if you just unleashed the floodgates and flooded Earth with all of the sun's ultraviolet light? It would actually have a sufficient flux to break down the cellular components of plants and land life. You couldn't
Is that-
actually, Jenna?
Oh, I was just going to ask, is that why they say to preserve the ozone layer because of the car emissions and the chemicals?
Yeah, so there's different types of ozone. There's good, ozone is ozone, but when we talk about ozone levels as pollution, that's ozone in the troposphere, which is bad for us because we're breathing it. The ozone in the stratosphere is extremely important because that protects us from ultraviolet flux. Now, in the 90s, in the 80s and 90s, we developed a hole in our ozone layer from these emissions like chlorofluorocarbons. And somewhere in this slideshow, a little later on down the line, I had a picture of this. This is actually an environmental success story. Regulations have since somewhat repaired the hole in our ozone layer. Here's something really scary. So here's 1980 and here's 2000 roughly, right? And ozone has a really, really trace abundance in our atmosphere. You see that 100, 200, 300? That's probably parts per million, meaning you get 100 ozone molecules for every 1 million nitrogen molecules, okay? So it's a very small abundance. But you can see it depleted from like 300 parts per million to 100 parts per million. And for reasons that I don't fully understand, this hole in the ozone, which was caused by like air conditioning and car emissions, chlorofluorocarbons, they went up into the stratosphere, they chewed apart and ripped the ozone apart, and they couldn't get themselves out of the stratosphere because there's no convection. For some reason that I don't understand, the hole in the ozone layer drifted right over Antarctica. Can anyone think of a reason why that's not good?
Melting. It melts.
Yeah, all that ultraviolet flux is gonna hit those ice caps, and that's not good for us. I don't have a graph showing you its current level, but it has since gone back up thanks to regulations on chlorofluorocarbons. Now, this problem is only tangentially related to today's global warming climate issues. That's something I'm gonna get into eventually, but we'll probably have to carry ourselves over. Today, I want to focus a little bit on the physics. Okay, so let me take some notes so that we have something concrete to go off of. I'm going to erase this, okay? And then I need to kind of get into some of the math formulas, because I do have a homework to do with you today, and there are a couple of new math formulas for me to introduce. Actually, you know what? I'll get to this stuff later. I've got 10 minutes of lecture left. What I would like to do is you have two math formulas in this chapter, and I'm just going to awkwardly introduce them right now so that our homework today goes smoother and more efficient. I think you guys will appreciate that. So one of the things we're going to focus on is, how does a planetary atmosphere heat up in the first place from sunlight? And we're going to kind of look at the effect that greenhouse gases have on that as well. But the first thing we have to do is we have to just answer a basic question. What makes a planet or a planet's atmosphere warm? And there are sort of three factors that come into play. Distance from the sun. That affects your amount of sunlight that you get. Two is something called your planet's albedo. This is a new vocabulary word for you. The albedo, which I'm going to use the letter lowercase a for, is basically your percent reflectivity to the sunlight. An albedo of 0 is 0% reflective, so it absorbs every photon, and that would be a pure black substance, of which there is no such thing as completely pure. There is no such thing as a 0 albedo surface. It's an abstraction. An albedo of 1 is 100% reflective, and that would be the purest of pure white, or sometimes I like to refer to it as a disco ball, okay? A disco ball, in theory, would have sort of an albedo of 1 because it reflects all the light that strikes the surface. Actual substances fall somewhere in between, and I have a lovely slide to demonstrate this to you. Bear with me, students. Where's my picture of albedos? Come on, damn it. Here we go, slide 41. So just take a moment, since you're learning about albedo for the first time, and let's enjoy, you know, some knowledge about albedos. Fresh snow without any dirt, which is very rare in the solar system, has high albedos of 80 to 90%. Have you ever gone out after a snowstorm and gotten snow blindness where you can barely see because of all that? You have to put on your sunglasses, right, after a snowstorm because it's so bright out. Crops, grassland have an albedo of somewhere around 25%. You know that it's warmer in cities because the albedo of asphalt and concrete drops to 5 or 10%. And this makes the rock warmer, and it makes it more effective at radiating infrared light. 2/3 of the Earth's surface is covered with water. Water is really interesting because its albedo will vary dramatically depending upon the angle of the sun. When the sun is high in altitude, the sunlight can penetrate deeper and your albedo drops. When the sun is low against the horizon, if you've ever been in a boat in the water near sunrise or sunset, the water almost becomes as reflective as a mirror, and you can actually get really bad headaches if you're a sailor and are out sailing around sunset because of the reflectivity of the sunlight off the water. What color is the moon when you look at it in the sky? This is not supposed to be a hard question.
White.
Right, white. But according to this graph, Ian, what substance on Earth does the moon's albedo most have in common with?
I guess asphalt.
Or blacktop, right?
Yeah.
So I don't get it then. Is the moon's surface white or is the moon's surface dark?
Well, I mean, so yeah, I don't really know how to answer that.
Have you guys, you've seen those pictures, right? Of, those pictures that were faked, but in the studio. I'm just kidding. Wait, let me keep this open here. Let's look at Apollo astronauts on the moon. Let's get some of those iconic. Oops, sorry. Okay. This is a picture I'm thinking of. I want more pictures like this. Let's get a really high resolution. I've got a few in my slideshows. I probably should just use that. Let's pick this. Let's get a really high resolution image. Okay. When you look at the surface of the moon in these images, the moon dust, the regolith that we studied before, it looks kind of grayish, right? But actually this is a good picture to choose here. Let's look at the very high resolution version of this. Whew. Look at that moon dust that you see down there. Like when you go to a beach on one of those sunny days and the sunlight's pounding overhead and just making the sand kind of blindingly white to look at? Could you imagine what it would be like to walk on the surface of the moon? There's absolutely no atmosphere above you. Not only is every single drop of sunlight coming down, all of the ultraviolet flux, the X-rays, the solar wind particles are all beating down. It would be like the sunniest damn day that you've ever been to on the beach. The surface of the moon is actually jet black. It's jet black. But the sunlight is so intense bouncing off of it. Remember, the sun's color from space is white, right? So you're just seeing that 5% reflected sunlight is still bright enough to make the moon's surface look white. But the moon's surface is jet black volcanic rock. Remember, we learned that those lunar maria are volcanic features, right? The third thing that's going to matter is greenhouse gases. And greenhouse gases are gases that are effective at absorbing infrared light from below. They are effective, extremely effective at absorbing infrared light. And they include carbon dioxide. Believe it or not, water is a very potent greenhouse gas. Clouds actually make the planet warmer. Methane to some degree as well. And there are others, but these are some of the big ones that matter for our own atmosphere and for the atmosphere of Venus and Mars. For a second, we're going to focus on these two factors. Explaining the greenhouse gas bit, that's complex, and we'll save that for next class. Today, I want to focus just on how warm will my planet be if you ignore greenhouse gases and you just focus on sunlight and albedo. So we're going to analyze that first. I know I'm running out of time here, but can I erase? Okay. So let's imagine, before I erase that, let's imagine this problem here. We're actually going to weirdly ignore atmospheres for just a second, and we're going to ask the question, how warm is my rock in space? And the moon would be a perfect example for us to try. So you've got the moon. It has absolutely no atmosphere and no greenhouse gas to affect the problem. All it has is sunlight beating down on the rock. By the way, when you think of it as being warm outside or cold outside, you're usually thinking of the temperature of the air because that affects your psychology. But in this case, if you were on the moon, in the vacuum of space, there is no temperature because there are no particles. What do I mean by the temperature of the moon? I mean, if you took your space glove off and you put your hand down into the moon dust, how warm or cold would that feel? All right. To answer that question, we have to use a formula called the no greenhouse temperature. It's one of the two formulas you're going to be using this week. The no greenhouse temperature answers the question, how hot is my airless rock in space? Okay. The temperature is a reference temperature, 280 Kelvin times the fourth power of 1 minus the albedo. Please note here that A stands for albedo, not for semi-major axis or something else like that, all right? Divided by the distance squared. And there's another trick here. The distance is measured in astronomical units to make the problem really, really easy. Let's try a quick example. The moon. You guys know the distance already, right? Oh, this is distance from the sun. For the moon, what should my distance be?
I mean, it's roughly 1 AU, right?
Yep. What did we decide the albedo was?
5 to 8%.
Sure. Let's go in the, we'll go with 7%, okay?
Oh.
Well, you were correct. You were absolutely correct. So as a percentage, the albedo is 0.07, correct? All right. So our temperature is 280 Kelvin times the fourth root of 1 minus 0.07 over 1 squared, which is 1. In the interest of time, I'm going to walk you this calculation. Calculators out. Let's do the inside of the fourth root first. 1 minus 0.07 equals. Okay? Now, if the distance was not 1, we would do divided by 1 squared equals. That's just showing you how you would proceed if there was a distance. Now we're going to do the fourth root. Remember, to do the fourth root, you have to hit shift and then this key here. So shift arbitrary root 4 equals. And now I'm going to multiply that backwards by 280 times 280. $275 Kelvin. Is that temperature random? 275 Kelvin? What would that be in Celsius? Remember, Celsius and Kelvin are the same with a 0-point shift, right?
The freezing temperature of water?
Isn't that wicked close? It's 2 degrees Celsius above the freezing point. Jenna, why would I find that so interesting? That the surface of the moon was just 2 degrees above the freezing point of water.
Because does it speak to the composition of it, or just how cold the moon is? Or
I
that
wouldn't
there's,
say that's cold. I would say that's quite warm compared to outer space.
yeah.
What would have happened if it was below freezing? Water would be in the form of ice. See, Jenna, my way of thinking about this, because I'm thinking about like the formation of the solar system. Let's go to that page here. This will be my last point, and then we can take a tea break. I really like this. I like this Wikipedia illustration here. I don't know who did this, but they were cool. I was thinking when the Earth first formed, the Earth probably looked a lot like the surface of the moon, except for one thing. It had volcanoes, right? So it had craters, it had jet black basaltic rock, and it probably also had active volcanoes. And what were those volcanoes pumping out?
Gases, CO2, stuff like
And CO2 and what else?
that.
Freaking water.
Yeah.
But Earth is at just the right distance where that water can sort of condense into a liquid. It's just above the freezing point under atmospheric pressure. Suppose the moon had been, or suppose the Earth, the early Earth, had been a little bit farther away. That H2O getting pumped out of volcanoes, should it collect on the surface, would have frozen in the form of ice, just like Mars has ice caps today. Suppose Earth had been a little too close. Then, as it did on Venus, all of that water would have gone into the form of steam. You guys know what I'm talking about, right? I'm talking about the Goldilocks zone. That's what this means to me. Have you heard that term before, the Goldilocks zone? The idea is every star has a key range of distance from it that could support liquid water, and liquid water, we believe, is the key to life forming on a planet. And different stars have different Goldilocks zones. Earth happened to form perfectly within the Goldilocks zone. Let's see if we can do this. Goldilocks zone. And if we just called up an image, there's probably all kinds of different cool pictures here. I always like to think about this in terms of our own solar system. Let's see if I can find a higher res map than this. I still haven't I haven't picked my favorite habitable zone or Goldilocks zone picture yet. I kind of like this crappy one here. We believe that Earth is just perfectly positioned in that range of distances which could support liquid water. Venus is just barely on the inside of it. Venus almost could have been there. Mars too. Mars is just a little bit outside of it. In fact, you guys saw at the surface of Mars that at one point Mars probably had liquid water at its surface, right? So Mars is actually more in the habitable zone than Venus is. Venus is a little too close to the sun. I've got so much more to teach you, and there's another formula, but I'm out of time for today. I wasn't very efficient today. I apologize for that. In any case, you've learned some things. There's more stuff for us to learn, but we're going to try the homework anyways. So it would have been nice if we had one more lecture session before hitting this homework, but this is the way the cookie crumbled, so we're just going to roll with it, okay? There's one new formula. I'll teach it to you as we go, and I'll explain the concepts next time. So let's give ourselves a little pause, as we like to do. It's now, oh Jesus, 1:40. Maybe 1:55, we hit the homework. Sound like a plan? Okay. I'll see you guys in a few. Okay, I'm back. I spent my tea break reading the Wikipedia articles on the great oxygenation events and the rise in the geological history of Earth's oxygen concentrations, I realized by talking to you, Ian, that I was woefully ignorant. I knew that there had been a spike in the concentration of O2 in Earth's atmosphere, but I didn't know what caused it or what caused it to decline. And unfortunately, tea break wasn't enough time for me to answer all of those questions. I'm not sure that they're completely answered anyways, but that spike in oxygen occurred during the Carboniferous period, roughly 350 to 300 million years ago. And some of the dominant landforms were not only amphibians at the time, but they had giant dragonflies with giant predatory, probably meat-eating dragonflies with wingspans up to 70 centimeters or more. Now think about it. 70 centimeters is getting up to about a meter, right? I can think of nothing more terrifying than being attacked by a carnivorous giant dragonfly. That would probably, or a swarm of them. Imagine a swarm of them. That would probably be a really scary thing.
If you think that's bad, there were also like, I want to say like 8 feet long centipedes and stuff. And yeah.
Great time for entomologists.
And that's actually something that I think is really interesting is
oh no, my horses got out of the paddock, Ryan. Okay, that's fine, Ryan, but please try to catch this video later and fix this up. You go tame those wild horses, cowboy. But please don't forget to do this homework later, okay? Okay. All right, Ryan, and don't forget that there's another version of this from last semester. If you don't feel like waiting for the video to render, it should be essentially the same, okay? Guys, we'll let Ryan capture his horses. We'll get on to the business of today, which is homework 11, problems from chapter 10. Let's do our usual stuff here. We have our name, Astronomy 1010, so I know who you are and how to find you, along with your section or whatever. This is homework, I'm sorry, did I say homework number 11? I think I meant to say homework number 10, correct?
yeah, it's 10.
All right, sorry about that. Homework number 10 are problems from chapter 10. Do you have them available, Ian?
Yeah, 52, 57, 61, 62, and 65.
All right, let's get right to it so we can be as efficient as possible. Chapter 10, number 52. Hopefully we learned enough during our lectures to do a decent job answering them.
52 says it is a swiftly rotating Venus is the title. Suppose Venus rotated as rapidly as Earth. Briefly explain how and why you would expect it to be different in terms of each of the following: geological processes, atmospheric circulation, magnetic field, and climate history.
The geological processes.
Geological processes, atmospheric circulation, magnetic field, and climate history.
Okay. So right out of the starting gate, I realized that we have not had enough lecture to fully answer this question. This is actually a very, very complex word question. If I haven't mentioned it up until now, Venus has a ridiculously slow rotation period. In fact, I want you guys to check this out. Just look at some stats with me on Venus from the Wikipedia page. Its orbital period around the sun is 0.62 years, or in days, it's 224 days to go around the sun. But let's look at its rotation rate. Forget about the negative for a second. It actually rotates opposite. It actually rotates slightly clockwise, which is unusual. But its rotation period is 243 days. Do you guys get my point here? The rotation period is 243 days. The orbital period is 224 days. So what am I saying, Jenna?
It's similar to the Earth in its rotation period, but drastically different in its spinning period.
Hold on, wait a minute. We got to use these terms correctly.
Yeah.
When we say rotation, we usually mean
Around-
axial rotation. Okay, so this, Jenna, anytime we use the word rotation, I'm going to think this.
Oh, okay.
If you want to talk about its orbit around the sun, say orbital revolution or orbital period, something like that.
Okay.
If you say rotation, I'm going to think planet spin. Okay.
Yep.
Okay.
So
So let's come up with see if you understand my point. Its orbital period around the sun is 224 days. Its axis spin, its rotation, is 243 days.
So its rotation is drastically different from Earth, but its orbit is pretty similar.
Well, 0.6 versus 1. I wouldn't say it's super. I mean, Venus is closer to the sun, so it's going to have a different orbital period. But I think you're missing my point.
A day on Venus is longer than a year.
That's my point. A day on Venus is longer than a year on Venus. Think about how weird that is relative to Earth. We spin on our axis every 24 hours. We have 365 something days a year, right? But on Venus, you go around the sun before the sun even spins in your sky. Could you imagine how weird that would be if you were like trying to track a day on Venus? The sun would probably just kind of sit in one place in the sky. And I'm actually trying to think about this. I've gone through this in my head before, but I've forgotten now. The sun's motion through your sky would be due to your orbit around the sun primarily. Remember that on Earth, the sun actually drifts backwards along the ecliptic. So I'm pretty sure you'd see the sun very gradually going from west to east. The sun travels eastward along the ecliptic, right? Venus travels eastward along the ecliptic. So you'd actually see the sun traveling eastward very slowly due to the orbit of Venus. And since Venus rotates backwards, it'd get an even more easterly component to it. The sun would probably for just hours sit in the same position on the sky, and that would really bug you out. This question is also asking about some other complicated things like magnetic fields and atmospheric circulation. And I hadn't quite gotten time to explain all of that to you, but I suppose we could do a little cheesy version of it now. First, let's talk magnetic fields. Why does a planet have magnetic fields in the first place? It's because of its rotation and the fact that it has some hot, metallic, liquid slush somewhere down inside of its core. Here's a toy, a basic child's electromagnet, which is worth considering. Remember that at some point I taught you that when current flows through a wire, it generates a little wimpy magnetic field in a circular pattern around it. If you attach a wire to a simple 3-volt D battery, and you were to coil it into a coil, you'd get a really, really wimpy dipole magnetic field, which kind of looks like some bunny ears. In an electromagnet, you wrap that wire around a lump of iron. Iron is what's called ferromagnetic, meaning it's not naturally magnetized, but in the presence of a magnetic field, it becomes magnetized and adds to the magnetic field. To make an electromagnet, you wrap your loop of wire around a lump of iron. The little tiny wimpy ass magnetic field from the wire induces magnetism in the iron, and then the iron becomes a powerful magnet, which is turned on by that little current. This is an electromagnet. In a way, Earth and Venus's interiors are actually quite similar. You've got a big lump of iron, which is ferromagnetic. Part of Earth's core is partially molten, so it's hot, melted iron, which probably has ionized bits in it, free charges flowing around. And as Earth rotates 24 hours a day, you're slushing those charges around, you're magnetizing the core, and you're creating a giant dipole magnetic field. Now, the Earth's so-called dynamo effect is a little more complicated than this, but that's the basic idea. What do I need for a planet to have a magnetic field? I need a very hot interior with liquid iron and ionized bits. but I also need rapid rotation to spin those charges around in a circle. Venus rotates so slowly that it is effectively not rotating at all. And because of this, Venus, despite having a hot interior, does not have a magnetic field. That turns out to have a profound impact on the history of planets. Why? Because magnetic fields, or what we call magnetospheres, are actually protective bubbles that protect a planet from ionizing radiation from the solar wind. This is something I had to study a lot in grad school because at Boston University, they have a lot of specialists in this area. Let's just type magnetosphere into Google and look at a couple of the pictures that come up. So one way to think about it is that Earth's magnetic field, it's kind of like a little magnetic bubble or shield. Every day, the sun is not only giving off radiation, but it's kicking out high-speed protons and electrons which fly throughout our solar system. They would normally rain down on the atmosphere of Earth, busting apart oxygen and water molecules, but instead they hit the magnetic bubble and the charged particles get sloughed off and around the magnetic field, kind of like hair blowing in the wind. Yes, some of those particles will spiral down and create a little aurora borealis, but without this magnetosphere, every day for billions of years, Earth's atmosphere would be harassed by that solar wind. This turns out to have had a profound impact on the history of Venus's climate. As the picture I'm about to show you demonstrates, at the end of our lecture today, we learned that Earth was in the right distance from the sun, such that it was in the Goldilocks zone, and a lot of the water that outgassed from volcanoes was able to condense into oceans. Now, I never ended up telling you the secret of Earth's carbon dioxide, but it's going to come up in today's homework anyways. It turns out that water plus silicate rock combine with CO2 and create carbonate rock on the seafloor bed. Earth actually has a Venus's worth of CO2 totally encrusted into the bottom of the seafloor. If Earth's oceans didn't exist, we would have the same concentrations of CO2 that Venus had, and life would not be possible here. The magic combination of liquid water, erosion, and CO2 trap CO2 so we can get it out of our atmosphere. Now, imagine you're Venus and imagine how things got a little bit ugly for you. You're a little bit closer to the sun. Temperatures are high enough that as you outgas CO2 and water, your water is going to exist in the form of vapor or steam. Not a lot of it's going to be able to condense on the surfaces. And you guys know what a water molecule looks like, right? Here it is. It's an oxygen with two hydrogens stuck to it. Now, add the fact that Venus has no rotation and you have a perfect shitstorm on your hands. Because what's going to happen is those high-speed solar wind ions, those little bullets that are protons and electrons, are slamming into your atmosphere, which has water vapor in it, and they smash apart those water molecules, kicking off the hydrogens into space. Today, Venus barely has any water on its surface at all, like none. But it certainly will have outgassed a lot of water. All of that water got stripped away by the solar wind. There's one last piece to this puzzle, and then we can start writing, because I'm sure you're eager to get on with it. Atmospheric circulation on Earth is very different than atmospheric circulation on Venus. And I'm sorry to give you all these different concepts at once, but this is sort of the way the cookie crumbles here. Convection takes place in the atmospheres of planets. Although this picture shows Earth underneath it, this was a mistake on the part of the illustrators in the book. They should have put Venus underneath here. This is how atmospheric circulation works on Venus. Sunlight strikes the equator of Venus more effectively than the poles. So you start off by heating up the equator. Warm air rises, it displaces cold air, and a giant circulation cell sets up. It's basically just convection, but when convection happens in a planetary atmosphere, we name it after the guy who first described it. They're called Hadley cells. Venus has one big Hadley cell, one in the northern hemisphere, one in the southern hemisphere. And that single convective cell is so effective at mixing up temperature that essentially there is no difference in temperature between the poles and the equator on Venus. This is not how circulation works on Earth because of its rotation. When you add rotation to a planet, you add this twisting effect that you've probably never heard about before. You study it in a basic physics class. It's called the Coriolis Effect, and it's a twisting force that happens in a rotating coordinate system. I'll spare you the deets, but basically Earth's Hadley cells get split and fractured into a set of triple Hadley cells. You guys have heard of like tropics versus temperate zones versus polar regions. The reason why Earth has these three mini climate zones is because each Hadley cell is kind of like its own separate refrigerator that keeps temperatures fixed in these different zones. It's always going to be cool at the poles. It's always going to be warm in the tropics. And where we live in the temperate zones, it's somewhere in between. This is super, super good for the history of Earth in terms of keeping water in somewhat of a liquid stage. There have been times where Earth went through a global ice age and temperatures froze and ice caps kind of advanced down this. They call it snowball Earth. We know that Earth has had a couple of these periods. These triple Hadley cells always help us keep a little bit of water along the equator, which is really good for regulating our carbon dioxide. Even if global temperatures got too high on Earth, we'd probably be able to keep some liquid water near the poles, and that would be good for life as well. Venus has none of this mechanism. All of those things contribute to make Venus a crappy place to live. No rotation, no circulation. Despite having a thick atmosphere, there's no erosion on Venus. There's no water, there's no ice, and without rotation, there really aren't any windstorms either. What if Venus started to rotate? What do you think would happen here? Let's see if you've learned enough. First of all, let's deal with this last. Let's talk about magnetic field. What would happen to Venus's?
It would like increase, it would
activate. It would actually turn on, right? How about the atmospheric circulation?
It would break down into thirds, or
what we call triple Hadley cells, right? Okay, now knowing your 4 geological processes, Jenna, from last class, let's go through our mind and think about which geological processes would be affected.
erosion, definitely, because we'd have
definitely activate some wind erosion. Would volcanism be affected?
Yeah.
Volcanism requires a thin lithosphere with cracks or vents. Venus already has a thin enough lithosphere for volcanoes to exist. Do you remember I showed you that picture of Mat Mons, the tallest volcano on Venus?
Yep.
I don't think rotation would affect volcanism, but Venus would still continue to outgas. I think basically volcanism would just proceed unaffected. That's my intuition. How about impact cratering? Would that be affected?
Yes.
To an extent.
Walk me through it.
Ian can take it. My thought process was just since it has a magnetic field, maybe there would be less.
Magnetic fields don't deflect rocks in space.
Okay.
Rocks are electrically neutral. They cannot be deflected by a magnetic field.
I was just gonna say, like, it wouldn't be a huge impact, but we wouldn't be able to see as much impact cratering, and the smaller ones would dissolve in the atmosphere, right? Although
Well,
I guess
Venus already has a super thick atmosphere.
Yeah, true. Okay.
Well, I guess I would say that impact cratering it's not really affected.
Well, erosion wears down craters, but remember that the bigger issue is that Venus doesn't show a lot of impact cratering today anyways, right? If you look at Mars, like we did last week, its entire southern hemisphere is covered in heavy bombardment, correct? And you could see when we looked at those craters like Schiaparelli, that erosion had chipped away a little bit at the craters. An increase in erosion will reduce cratering, but the problem is Earth and Venus virtually have no large-scale impact craters at all. So craters would be a teensy bit reduced, but there's hardly any cratering anyways, right? Now for the really complicated part. Plate tectonics. Does Venus have plate tectonics today? Yes or no?
I mean, I'm gonna guess that it might, since it's not frozen over like Mars is.
What's the number one indication of plate tectonics on Earth? You're looking
Like-
at it.
Yeah, like shapes, continents.
Continents. Do you
breaks
see those on Venus?
No, not really.
No. For some reason, despite Venus having a thin enough lithosphere for volcanism, Venus lacks a global set of plate tectonics. And think about how weird that is. In order to have plate tectonics, you need to have a thin lithosphere so you can fracture it. But for some reason, Venus's lithosphere doesn't fracture like Earth's. And the answer to it can be seen plain as a pikestaff if you go back and look at where the boundaries of plate tectonics are on Earth. Remember this picture? We even talked about it. Where do you see all the boundaries of Earth's lithospheric plates taking place?
Over water.
In the water. The water is lubricating the rock and helping it to fracture. If Venus doesn't have oceans, if it doesn't have large-scale surface water, its surface becomes like clay baked in a kiln. It's cooked dry to the point where it cannot form large lithospheric plates. Okay, volcanoes can still kind of poke through, but you need water. Now, let's go back to our swiftly rotating Venus. You've got erosion, you've got Hadley cells, you've got a planet which is hot along the equator, maybe slightly cooler at the poles, and you're still pumping out volcanoes which produce water. What do we think? What would be a possibility there?
It's becoming similar to, wait, well, I'm forgetting the question, but like it's becoming similar to Earth.
Yeah, it probably won't be Earth 2.0, but I could imagine if you could create those triple Hadley cells so that Venus could have a polar region which was cold like Earth's, maybe some of that volcanic outgassing could condense into some liquid. Instead of ice caps, you'd have ocean caps, right? Ocean caps. And perhaps those ocean caps could trap a little bit of the extra CO2 in Venus's atmosphere. Would it become Earth 2.0? No, it would not. But it would be a cooler planet with more interesting climate and at least the possibility of a tidbit of liquid water. Rotation turns out to be hugely freaking influential on the development of a planet. And that's not something that you would expect. That's what makes this question complex and cool. Okay, let's put this into a paragraph form. It's going to suck, but we're going to do it. All right. Sorry, this question is one of the hardest ones in the entire class, to be honest.
It's really interesting though. So
I think so. I mean, you know, I study this stuff. I think it's interesting.
Yeah.
I was even thinking earlier that like if you could change like a few things about Venus, you might be able to terraform it into like a
If you
biome.
could spin it up, you might actually be able to do that. If Venus had, let's put it this way. If Venus were to rotate as swiftly as Earth, a number of factors would change to create a more hospitable climate. And now we're going to go into those factors. First, rotation would increase atmospheric circulation leading to wind erosion and the creation of a set of, here's a key concept, triple Hadley cells. I'm going to have us underline triple Hadley cells because that was like a key concept of which we were not previously aware. The Hadley cells would lead to a range of temperature zones, including cooler poles. Second, rapid rotation would activate Venus's, is that how I do this? Venus's magnetic field, which would allow, second, rapid rotation would activate Venus's magnetic field, which would allow outgassed water molecules. Okay, I'm going to have to kind of head back up to the top here. Which would allow outgassed water molecules, let me go down here, to stay protected from the solar wind. My sentence construction is kind of crummy today, which would allow outgassed water molecules to stay protected from the solar wind by Venus's magnetosphere. I want to include that term because that's another nice vocabulary term. By Venus's, the term is magnetosphere. Hopefully you guys can read that. I'll head up to the top now. Can I take off a chunk up here without complaint? Okay. So continuing on, if some of this water could condense at the poles into, let's call them ocean caps, Venus might trap some of its excess CO2 into carbonate rock. I'll talk more about carbonate rock in our next lecture. Might trap some of its excess CO2 into carbonate rock and further reduce temperatures. It's possible to imagine a small amount of plate tectonics to develop with a fractured lithosphere. So I'm kind of just awkwardly throwing these things in here. Now at the end, we'll kind of summarize it. Can I erase? Does everyone have the bottom stuff? Okay. All in all, a swiftly rotating Venus would have a cooler climate that might be more hospitable to life. And yes, Ian, it suggests that if we could somehow spin Venus up, we might be able to allow it to terraform itself. I'm not sure how we would do that, but
Definitely not achievable at the moment.
yeah. In fact, one of the big mysteries of the formation of our solar system is, since all of the other planets spin rapidly, somewhat rapidly, the only mechanism you can really imagine for Venus to not be rotating is it must have gotten clunked by a couple of overgrown meteoroids, some real big ones, at just the right angle to kind of spin it down. That's the normally when things contract and form, they naturally begin to rotate, which is why planets spin, which is why the solar system spins. It's hard to imagine something contracting and not developing rotation. So something must have really clunked into Venus at some point to slow that thing down. That's the only mechanism I can imagine. By the way, do you guys know what the rotation period of Mars is? It's pretty much exactly 24 hours.
I was going to say, I think it's slightly less or more. I thought it was less.
I think it's more. That's something I should know. I don't know if it's going to come up in our homework today. I just want Mars. Oh, it just it had it there for a second, like the day. Rotation period. Where is it? "24 hours and 37 minutes. Shoot, did I lose Ian? Okay, can I erase all this? Do you guys have it all? Talk to me, peoples. All right, I'm erasing. Jenna, can you read 57?
Yep. 57, feedback processes in the atmosphere. As the sun gradually brightens in the future, how can the CO2 cycle respond to reduce the warming effect? What parts
Yep, keep going.
What parts of the cycle will be affected? And in this, I'm sorry, is this an example of positive or negative feedback?
again, this problem is another problem that would have benefited from more time in lecture. Luckily, there's a slide that can basically answer this entire question. The way we're going to format this question is instead of writing an essay, we're going to do it like bullet points because it'll get the concepts across in a more efficient way. Let's take a look at how CO2 gets trapped in Earth's atmosphere in this lovely little slide that I've got here. It's called the carbon dioxide cycle of Earth, or the CO2 cycle. The picture from your book is actually very nicely done. Another moment where they really got it right with their graphic design team, because the visual is just so clear and explains so much. So we know that Earth has active volcanism. And although you don't hear about it in the news, volcanoes go off on Earth every single day. We tend to only hear about them when they cause disaster. They output CO2 and water into our atmosphere. And a lot of the water condenses into precipitation, rain, snow, and CO2 can actually dissolve into water. Anyone who's drank a can of polar seltzer before knows that. That's what you have. You have bubbles, CO2 bubbles dissolved in water. When CO2 dissolves into water, it actually makes water slightly acidic and capable of chipping away and dissolving rock very effectively. So this slightly acidic rain washes down over the continents where we have silicate rock. It dissolves silicates. Just think of those muddy rivers you might have seen before, like the muddy banks of the Mississippi. That's all brown sediment and silt that's being washed out to sea. The water plus the CO2 plus the silicates all combine on the seafloor bed to make carbonate rock. An example of carbonate rock would be limestone. Coral reefs actually contribute to a large fraction of it as well. But let's just look at a picture of limestone for a second. The New England farmers call it quicklime. Some people might even spread it on their lawns to help combat the acidity of rain. In fact, you'll notice that this limestone, you can actually see the encrusted shells of organisms in this limestone. A lot of seafloor organisms, from coral reefs to other mollusks and things, they incorporate carbon dioxide and water and rock into their shells. This carbonate rock traps a whole lot of CO2 in Earth's ocean floor. By the way, think about it, a whole lot of CO2 that we wouldn't want released, right? And now, if we go back to my slideshow, the carbonate rock is trapped along the seafloor bed, but in plate tectonics, the seafloor bed is slowly moving at a few centimeters per year, being punched right down into those subduction zones where the lightest density materials, water and CO2, are turned into steam which melts rock and creates a new cycle of volcanism. How many of the 4 geological processes are involved in the carbon dioxide cycle?
3 of them, right?
That's right. Everything except for impact crater. You get volcanism plus erosion plus plate tectonics all working in this cool tandem to keep CO2 out of our atmosphere. By the way, a tiny bit of CO2 stays in our atmosphere, and that actually has a really profound effect on temperatures on Earth. Remember how today's lesson we learned that CO2 comprises 0.04 of 1%? That 0.04 of 1% CO2 is responsible for changing Earth's global temperature by 30 Celsius degrees. If it wasn't for that tiny fraction of CO2, our average global temperature wouldn't be positive 15 degrees Celsius, it would be negative 15 degrees Celsius. That would be less pleasant, at least for us. In any case, this can actually function like a little switch. And hear me out on this, because this is what this problem is all about. Where's the CO2 switch here? Okay. If Earth gets a little too cool, say we go into a global snowball phase where glaciers advance down the surface of Earth, you're actually going to get less precipitation and less CO2 dissolving into this rainwater. but you're going to keep pumping out CO2 from volcanoes, even as less CO2 is dissolved into the oceans, forming carbonate rock. The buildup in extra CO2 will actually increase the greenhouse effect and bring temperatures back into equilibrium. On the other hand, our question is going to explore this branch of the negative feedback loop. Warm temperatures not only dissolve more CO2 into the rainwater, but they create more precipitation, more erosion on the surfaces of the land. You form more carbonate rock into the seafloor bed, reducing the small amount of CO2 we have, and this cools temperatures back down. We believe this CO2 mechanism is one of the reasons that Earth has had relative climate stability for billions of years. Our oxygen levels might have fluctuated quite a bit, but our temperature levels have not, and that's good for life. So why don't we just reproduce this right here in some crappy little bullet points, okay? Okay. More sunlight equals warmer global temperatures. Okay? Warmer temperatures, they lead to more CO2 dissolved in rainwater, and also more precipitation, storms, and other effects. All of this means more carbonate rock is formed, and simultaneously we have reduced CO2 in the atmosphere. Less CO2 leads to a weakened greenhouse effect. And I want to be clear what I mean by a weakened greenhouse effect. Basically, what's happening in parentheses is less infrared light is absorbed by the atmosphere. This leads to reduced temperatures. And this is an example of a negative feedback cycle. This is known as a negative feedback cycle. And I think that that's a good answer for that question. Okay, the rest is math stuff.
By the way, sorry I ran out on you a second ago. I had to go to the bathroom real badly.
That's fine. I've been in that situation before. It's actually much worse when you're the teacher because it's sort of not supposed to stop, you know? I'm ready to erase if you guys can handle that. Looks like you guys are in a good spot. Okay, Kim, are you down to read us number 61?
Sorry, I was switching over and forgot to unmute myself.
That's okay.
Okay, 61. The mass of an atmosphere. What is the total mass of Earth's atmosphere? You may use the fact that 1 bar is the pressure exerted by 10,000 kilograms pushing down on a square meter in Earth's gravity.
Okay.
Remember that every square meter of Earth experiences this pressure from the atmosphere above it. Alternatively, okay.
Before you, I'm so sorry to interrupt. Can you tell me what it said after 1 bar? There was some other data that I wanted to have there.
Okay, 1 bar is the pressure exerted by 10,000 kilograms pushing down on a square meter in Earth's gravity.
This is what makes the problem really easy and yet kind of lame. I'll tell you why I thought this problem was worth us doing. Instead of actually starting with 1 bar, 1 atmosphere of pressure, they actually give you the mass sitting on top of a square meter. And I want you guys to all draw a picture with me, okay? So you can understand what's going on. Let's over here on the left, let's draw a circle to represent Earth. And now we know the radius of Earth, right? The radius of Earth is 6,400 kilometers. Okay, now I want you to imagine the atmosphere surrounding Earth. And I want you guys to imagine that I just took 1 square meter, roughly the size of this chalk dry erase board. And I want you to imagine me extending this square meter up into the atmosphere. So basically what I want you to imagine is, sorry, I got to get my perspective right. I want you to imagine a vertical column of gas sitting above your head with an area of 1 square meter. So I take this 1 square meter, I put it on the ground, and I extend it up into outer space. And basically what they're doing is they're telling you the mass of that entire column of atmosphere. Now, I think the problem would have been cooler if they forced you to get this number, which wouldn't have been that hard if you think about it. You know that pressure is force per unit area. And you know that the force coming down on a unit of area is mass times little g. And you know that the pressure is 100,000 pascals or 100,000 newtons per square meter. But what is little g?
Gravity? Oh,
Say it better. Little g is not gravity itself. Little g is discovered by Galileo. Huh?
I don't know if I'm not remembering this correctly. Is that the gravity of Earth?
That's not the right way to say it.
Okay.
First of all, little g is an acceleration. It's the local acceleration of Earth's gravity. I'm not sure if you guys understand the difference, but if you say the gravity of Earth, I'm thinking Earth has a gravitational force, a gravitational field, right? G refers to the acceleration that objects will experience if they drop to Earth. And little g, you may have forgotten, is 10 meters per second squared. What do you get if you divide 100,000 by 10? You get a mass per unit area of 10,000 kilograms per cubic meter. So if you divide both sides by g, your mass per unit area. Anyways, I would have liked them to have made you do that, but okay, anyways. So keep going, Kim. Tell us what they want us to do.
Hang on. Okay. Alternatively, you may start with the English unit value for the pressure of 14.7 pounds per square inch and convert it to kilograms.
Yeah. Okay. Never mind. I didn't realize they were going to talk to us about imperial units. PU, that stinks. Okay. Let's stick to metric units for a second, Kim. if I know that one column is 10,000 kilograms per cubic meter, how could I go about finding the mass of all of that atmosphere? I guess I'd have to multiply it by what?
However many meters of area there is on Earth, right?
How many square meters?
Square meters. Yeah.
If only I knew the formula for the surface area of a sphere. Ian, do you know the surface area of a sphere formula?
I should off the top of my head, but I don't. I know that there's a pi r. I think
Jenna
it's
knows it.
pi r.
Jenna's got it.
I think Ian was close. It's 4 times pi times radius squared. Is
Yeah,
that-
you know it's got to be r squared because you need square meters. Sorry, Ian, I didn't realize you were getting there.
No, it's fine. I was trying to remember which circle sphere formula it was. It's fine.
Yeah, there's a whole bunch of different. They have pies and they have anything with circles involves pi. If it's an area, you have to have r squared. Okay, let's work this out in square meters. Class, what is the radius of Earth if it's 6,400 kilometers? Oh, isn't Ian our resident dimensional analysis expert? How do I convert from kilometers into meters?
I think someone else has got it this time, right?
No. I think you should keep
Okay,
trying.
okay.
You're so good at it that we want to get through our
Okay, so we're converting that to meters. So that is times kilometers on the bottom and meters on top. And that would be 1,000 on top and 1 on the bottom.
Okay. Can we do that in our heads?
Yeah, that would be 6.4 times 10 to the 6th.
Meters. Okay. So the mass of our atmosphere then should be 10,000 kilograms per meter squared times 4 times pi times open parentheses 6.4 million meters squared. And I'll wait for you guys to give me the answer. Nori, don't tell me you forgot your calculator today. You look like a person who is not involved in calculations right now.
I'm not really home a lot lately, and I just grabbed my bag with my notebook and my iPad in it, and I always forget my calculator. So
Yeah.
I'm sorry.
Didn't I tell you to stick that calculator in your bag so you wouldn't
I
forget?
know, I did, and then I took it out, and then it was out,
Look,
and
you know what, Nori? I'm glad you're here with us anyways. I'm glad that you are existing alongside of us. This helps. All right. Did anyone get a number for me?
I got 5 times 10 to the 18th,
Units?
and that would be kilometers.
Well, oh, sorry. Look what I did there. I'm such a doof. It's kilograms per cubic.
Kilograms.
Right? I don't know why I did that. It's a mass, correct?
Yeah.
Okay. Up to now, you could be forgiven for saying, I don't give a shit about this problem. Why is this interesting? It's only interesting if you compare this to the mass of Earth. So I'm going to erase up here for a second. And now for the final thing that I'd like us to do, I don't think they asked us to do it, but I want you to do this. The percentage of Earth's mass of the atmosphere divided by the mass of the Earth, 5 times 10 to the 18 kilograms over 6 times 10 to the 24 kilograms. What you get? one significant figure will suffice.
8, -7.
Kim, help me write that out in decimal form.
Yep, sorry. 8 times 10 to the -7.
Right. And rather than write that down, I'd like to just write it out like a stupid number. So how many zeros do I need here? 0 point.
Would it
Here
be
we go.
6 zeros and then the 8?
Yeah. What that means, Kim, remember, is that this means the 8 is in the 7th decimal place
Yeah.
after the 0. So I would have to write 6 zeros, 1, 2, 3, 4, 5, 6, and then the 8. Now, what would that be as a percentage? How do I go from that into a percentage?
It would be 0.00008%.
So I get rid of 2 zeros.
Yeah.
0, 0, 0, 0. Yeah. That's what percentage the atmosphere makes of Earth.
Hemisphere.
It's truly insignificant. And that's not necessarily obvious before you do this problem, that the atmosphere of a planet makes up such a small fraction of its mass. Nori, can you read us problems? You want to read us number 62?
Okay. The role of reflectivity. By assuming 0% and 10% reflectivity respectively, find the maximum and minimum possible no greenhouse temperatures for a planet at 1 AU. What reflectivity would be necessary to keep the average temperature exactly at the freezing point? Compare this value to Earth's actual reflectivity at table 10.2.
Okay, let's start by writing down our no greenhouse temperature. The temperature of a planet, before we include the effects of the greenhouse effect, is 280 Kelvin times the 4th root of 1 minus the albedo over the distance squared. They've given us 3 tasks. 1, find the reflectivity of a find the temperature of a black planet that's completely absorptive, so literally a black body, like if Earth was this, if it was just a dark black sphere that absorbed every photon. They also want us to do a perfectly white planet, and then they want us to do a third job where we find what temperature would Earth need to stay right at the freezing point. I don't know if they asked us to do the black planet or the white planet first. I don't know if it matters.
It says to find the by assuming 0% and 10%. So
Wait, do they say 10% or do they mean 100%?
I mean 100%. I'm sorry.
Okay, yeah, that is because a white planet wouldn't be at 10%.
Yeah.
All right, so black planet is first.
So it would be the black.
The albedo is 0. All right. And this is all at Earth's distance, correct?
Yes. It's 1 AU.
All right. So we have 280 Kelvin times the 4th root of 1 minus 0. 1 minus 0 is 1, and what's the 4th root of 1? Actually, can we just write the whole thing out correctly? 1 minus 0 over 1 squared. 1 squared is 1, 1 minus 0 is 1, 1 over 1 is 1. What's the 4th root of 1? What's 280 times 1? Now you can see where the 280 comes from. The 280 is a reference temperature for a perfectly black planet at a distance of 1 AU. That's where the 280 comes from. A white planet has an albedo of 1. The temperature is 280 Kelvin times the 4th root of 1 minus 1 over 1 squared. What is that going to equal?
Um, 0.
That's right. 1 minus 1 is 0. Radical anything 0 is 0. Does that make sense, Ian? Planet would be at absolute 0.
Guess. I mean, if there's no atmosphere, then yeah.
If the photons are being scattered back into space, none of them are being absorbed. The planet's
Yeah.
surface does not get any energy. Therefore, it's perfectly cold. All right. All right. But in concept, no actual planet could be like that, of course. But yeah. Okay. Do you guys have this? Because I'm going to need some space for the third part. The next thing and the third thing we're going to do is we're going to re-engineer this problem to find what albedo we need to stay at the freezing point. And we're going to compare that to Earth. Okay, for the third part, at freezing temperatures, 0 degrees Celsius is 273 Kelvin. And I'm going to plug that in. And I'm going to divide both sides by 280. So I have 273 Kelvin over 280 Kelvin is the 4th root of 1 minus A over 1 squared. How do I deal with the 4th power? Oh, sorry. Damn it. I'm stupid and sleepy. To kill a 4th root, you have to
quadruple it, or
not quadruple. That means times 4.
yeah, you to the 4th on each side.
Raise it to the 4th on each side. So this will lead to, we can drop the units of Kelvin now. 273 over 280 to the 4th power is basically equal to 1 minus the albedo. How do I solve for the albedo now, Jenna?
Do you?
Something equals 1 minus A. Do you know how to handle that?
Oh, I see what you're saying. It's an equation. Yeah. You actually, no, I don't. I know you have to like move
This
the
is
one.
like the goddamn disease algebra problem ever.
Um,
15 equals 1 minus X. You don't know how to solve?
For X. Yeah, you would like subtract 1.
Well, that will leave you with negative A. I think of it as you add A to this side, right? And then you subtract this bad boy. All right. So A is 1 minus 273 over 280 to the 4th power. At least punch that in for me.
I got 0, 0.1, I guess.
Yeah, basically 0.96
Yeah.
is approximately 0.1 or 10% albedo. Remember when I showed you that picture from our lecture today? You might have not noticed it in the corner there. It was slide 41. The average albedo of Earth, according to this, is 31%. So 10% is approximately 1/3 of Earth's albedo of 31%, right? So Earth, if Earth was 3 times more reflective, we would be at the freezing point. Can you guys imagine a scenario where Earth would be 3 times more reflective? How could I make Earth 3 times more reflective? Huh.
I mean, it's kind of a loop, but if we were in an ice age, so if Earth's covered in
Yeah.
ice,
If the ice caps advanced, so that would actually create a kind of positive feedback loop, wouldn't it, Ian? That the CO2 cycle would need to fight against. Because as Earth's ice caps advance down the surface of the planet gets more reflective and less good at absorbing sunlight. That CO2 cycle would really have to go bonkers to try to counteract that. And it might take a while, right?
Yeah.
Climate science is very complex. Okay, we got one more to go. Speaking of raising global temperatures, the heat's on, it's getting kind of hot here. 1 second. Sorry, I was imagining Texas oilmen and Saudi Arabian princes getting rich as I sweat to death here. It was causing me some consternation. All right, I'm going to erase this. Last problem's a bit of a doozy, not going to lie. I think we're back to you, Ian.
sure, 1 sec. 65, escape from Venus. There's an A, B, and a C. A says calculate.
Let's do one at a time, okay?
Sure, yeah. A says calculate the escape velocity from Venus's exosphere, which begins about 200 kilometers above the surface.
Here's an escape velocity formula. We learned this in a previous class. It's 2gm over the effective radius, which means you need the radius of the planet plus the height. The mass of Venus is, I think, 5 times 10 to the 24 kilograms. The radius of Venus is 50 kilometers. You gave us a height of, what's the height of the exosphere?
I believe it said 200 kilometers. Yeah, it says that.
Huh. I wonder if Earth's exosphere begins there as well. Because remember, I had the top of the atmosphere close to like, they don't even have the exosphere in this. This shows our exosphere. I just want to compare it. Oh yeah, they have our exosphere beginning somewhere between 110 and 120 kilometers. So, all right, Venus has more atmosphere. That makes sense. Okay, let's first convert to meters, okay? The radius of Venus plus the height is 6250 kilometers. And because this problem's already long, I'll speed it up. Multiply by 1,000 meters per kilometer, and you get let's just call it 6.3 times 10 to the 6 meters. I don't really see a need for 3 sig figs, so I'm rounding 25 cents up to 30 cents, okay? The escape velocity then is the square root of 2. The gravitational constant 6 times 10 to the minus 11 meters cubed per kilogram per second squared times 5 times 10 to the 24 kilograms divided by 6.3 million meters. Why don't you guys punch them up? Anyone who takes the final exam will be doing this more than once on the final exam, by the way.
I got about 10,500 or
Oh,
so.
what are the units?
Um,
It's a velocity, Ian. Try to imagine some units of velocity in the MKS system.
is it kilograms squared times second squared? That doesn't
So
sound
you
right.
drive down the street at 95 kilograms squared times second squared?
No.
That sounds nuts.
Oh, duh. Meters squared per.
Jenna,
Meters per second.
thank you.
How I'm trying. Sorry, I was trying to do the math of it, and I'm like, okay.
Why don't you just think miles per hour, change
Yeah.
miles to meters and hours? Okay, anyways. It's customary to convert escape velocities into kilometers per second. How many kilometers per second is that?
We multiply that times 1,000.
All right, you need to do dimensional analysis then. 10,000.
Oh, we divide it by 1,000.
Fine, okay. So what's the answer then?
105. Oh wait, sorry. 10.5
Thank you.
meters per second.
Okay. Since you were capable of thinking your way through that, I will not force you to do the dimensional analysis. I'll presume that you could do it if you had to. Get that down because I'm going to need the whole damn board for part B. In fact, before I even let you read part B, Ian, remember how I had that cool flash animation today?
Yes.
I want you, oh, look, it's still bubbling away there.
Never close it.
Yeah, I probably shouldn't actually. You guys can see that not all the particles in a box move at the same velocity. Let's reduce gravity a bit here. Ooh. Now, like a real atmosphere, some particles are potentially boiling away from the exosphere. Particles in a gas obey a distribution of speeds. Some move fast, some move slow, some move in the middle, but it's not equal. That's not how nature does things with gases. Now, you're not going to like the sound of this very much, but I have to tell you, gases obey a Maxwell-Boltzmann distribution of speeds. What the F does that mean? It means that nature has her own particular logic about how many particles should move fast and how many particles should move slow. It kind of looks like a bell curve, but it is not symmetrical. It makes a bell, but there is the existence of a high-speed tail. There's always a few more particles traveling at high speeds than there are particles at low speeds. Why does this matter? It matters because particles in the high-speed tail are particles that are in danger of jumping off of a planet and achieving escape velocity. And you can see that right here in my, this is why I wanted this bloody thing so badly. Oh, come on. I've already lost it. Wait, here it is. you guys can see, let's add some, watch this. Let's play. Let's add some heat. And as I raise the temperature, notice that some of the particles with high kinetic energies, they can kind of boil away into space. This is fun, okay? Now, I wish I had had those kinds of visual aids when I was a student. They would have really helped me. One way you can characterize the velocities of the gas is because the velocities are always sort of different, it's customary to calculate this. The most probable speed tells you what the greatest number of gas particles are traveling at. And there's a formula that we're about to calculate. Actually, screw this. Let's just put it up on the board. This speed here is called the thermal speed. And that's what we're going to do in part B. I need to erase, okay? Before you read it, Ian, introducing the thermal speed of the gas, it's a representative temperature of the gas particles. And the formula is the square root of 2 times the Boltzmann constant divided by the temperature divided by the mass of the particle square root thereof. That's your gas particle. Ian, take it away.
All right. Part B says calculate and compare the thermal speeds of hydrogen and deuterium atoms at the exospheric temperature of 350 Kelvin. The mass of a hydrogen atom is 1.67 times 10 to the negative 27th kilograms. And the mass of a deuterium atom is about twice the mass of a hydrogen.
Because it's, excuse me, 1 proton and 1 neutron for deuterium. All right, for hydrogen then, the thermal speed is the square root of 2. The Boltzmann constant is 1.4 times 10 to the minus 23 joules per Kelvin. The temperature is 350 Kelvin. The mass is 1.7 times 10 to the minus 27 kilograms. Come on, folks.
I got 2400, and the unit, would that be joules per kilogram?
Hold on a second.
Oh,
It's radical joules per kilogram. But now you got to remember what a joule is, right?
mhm.
A joule is a kilogram meter squared per second squared. So what is radical joules per kilogram equal to?
Meters per second?
That's right. It's a velocity. How many kilometers per second is that? I thought you were going to get tripped up by the square root, Jenna, but you were too good. You canceled out your kilograms. You distributed the square root to meters squared per second squared. I'm impressed with you.
Thank you. And it's 2.4 kilometers per second?
Per second, right? All right. Now, let me show you a shortcut for deuterium because I'm feeling kind of lazy today. Maybe you guys are feeling kind of lazy too, huh? Okay, I know that deuterium has a mass that's 2 times the mass of hydrogen, correct? So watch this slick Rick maneuver. The thermal speed will then be the square root of 2kT over 2 times the mass of hydrogen, correct? Now, Jenna, you were pretty good at distributing the square root, correct? Imagine you distributed the square root to the radical 2, and then you pull it out front. In other words, this is 1 over radical 2 times the thermal speed of hydrogen that you just calculated. Do you see that trick? This way you don't have to punch it all in again. So take 2.4, divide it by the square root of 2, and what do you get? I don't always show my students that, but I was feeling generous. Which means
Is
lazy.
it 1.2?
No, come on. You can't do radical 2, buddy. 2.4 divide by 2 square root thereof. It's 1.7 kilometers per second. I don't know what you did. I think you probably divided by 2 and then square rooted everything, right? And that was a mistake. Yeah. In fact, you just divided 2.4 by 2 and you didn't even bother with the square root. Okay. Let's watch how I did that again. 2.4 divide by 2. Order of operations, parentheses come before multiplication division. Radical 2 equals. See that? Slick Rick trick. Okay. Now, we've got 2.4 and we've got 1.7. This is hydrogen. This is the thermal speed of deuterium. I'd like you to notice that deuterium is more sluggish than hydrogen. Why? Why are the deuterium atoms more sluggish than the hydrogen atoms?
They have twice the mass.
Heavier.
Exactly. All right. Now it's time for part C, the final part of today's homework. Ian?
Right, sorry. C says, in a few sentences, comment on the relevance of these calculations to the question of whether Venus has lost large quantities of water.
All right. There's no way you would even have a chance in hell at answering this question without some help from me. That's why it's good that I'm around, okay? First of all, this question is referring to a very famous experiment in planetary science. And it's deeply related to some of the things we talked about in today's class and homework. Up to now, let's take a look at what you guys have done. You calculated the escape velocity of Venus, which was 11 kilometers per second. That means it's like way the hell up here somewhere. You also calculated the most probable speeds of hydrogens and deuteriums. And sure enough, it's way lower. For Venus, it's like 11 clicks per second to escape. And the typical speeds of hydrogen and deuterium are around 2 clicks per second, right? So obviously the majority of these particles will not be jumping off of Venus. The problem is that there are still some particles up here in the high-speed tail. And ones that are close to or at the escape velocity will occasionally boil away and jump off of the gravity of the planet. In fact, that's what you can see happening here in my little flash animation. I'll reduce the gravity even more. And you can see that some of the particles are actually getting kicked off into space because those particles are in the high-speed tail. By the way, these gas particles are obeying a Maxwell-Boltzmann distribution. That's what's so cool about this, is you can see the Maxwell-Boltzmann distribution in action. Okay, what you need to do to figure out if a planet will lose its atmosphere over time is you need to apply the test for atmospheric loss. So we are going to apply the test for atmospheric loss. And the test goes like this. Is the thermal speed greater than or equal to, 1/5 of the planet's escape velocity? If the thermal speed goes over 1/5 is 20%. If the thermal speed goes over roughly 20% of the escape velocity, if yes, that gas particle will be lost over a geological time scale. We'll just say gas is lost over time. If no, the gas remains. In our case, 1/5 of the escape velocity is 1/5 of 10.5 kilometers per second. Punch that up, kids.
I got 2.1.
So for hydrogen, the thermal speed was, what was it again?
2.4 kilometers per second.
Is greater than 2.1 kilometers per second. So what happens to hydrogen?
Gas is lost over time.
Hydrogen is lost from Venus's atmosphere. In the case of deuterium, deuterium's thermal speed is 1.7 kilometers per second. Look how magic this is, which is less. So obviously the deuterium remains in Venus's atmosphere. Okay. Now, to answer the question, this is important, by the way. This is the kind of thing you'd have to do in a final if any of you decide to take my final. This is a key technique in planetary science today. I'm not telling you something esoteric. Everyone who studies the atmosphere of Mars, Venus, all planetary scientists, they play these reindeer games all the time. To fully understand the question, because you're still not there yet, you need to know about something called the cosmic abundance of deuterium. So if you go into outer space, let's go, for instance, to the Eagle Nebula, you remember that most of the gas in space is made of the same composition as the sun. What's the composition of the sun? That's a test question, by the way.
Hydrogen and helium.
What's the fraction of hydrogen?
77%.
That's nitrogen in Earth's atmosphere. It's
Or no,
7%.
Sorry. What?
Okay. Earth's atmosphere is 77% nitrogen.
Yeah, I was trying to remember which 70 it was.
It's 70% hydrogen. But here's the thing, Ian. Since hydrogen is less massive than helium, helium's 4 times as massive. It basically works out of, this gas is made of 9 hydrogens for every 1 helium. So most of the atoms in this gas are actually hydrogen, okay? Now, work with me. Throw away the helium, leave only the 70% hydrogen, 9 out of every 10 atoms, and just count through those hydrogen atoms. You will find deuterium in there. because it's left over from the Big Bang. That's where deuterium comes from. The cosmic abundance of deuterium is you get one deuterium atom for every 6,000 hydrogens. One deuterium for every 6,000 hydrogens is known in physics and astronomy as the cosmic abundance of deuterium. And by the way, the water in this Windex bottle also has one deuterium for every hydrogen. You understand what I mean, right? Like if you go to Earth's oceans and you measure seawater, 6,000 of those water molecules will be H2O, and one out of every 6,000 will be, I don't know what they call it, DHO or something. It's a heavier version of water that has a deuterium stuck to it. Now, what if I told you that during those Russian space missions, cue up a slideshow here. Last class, I told you that Russians managed to land on the surface of Venus. Where are you, you bloody jerk? Oh, this is before my slideshows were cool. Astronomy. Hold on a sec. Thank you. There we go. I told you that the only times we ever landed on the surface of Venus is when the Soviet Union Space Agency, they basically crashed 11 of their satellites into the cloud tops of Venus before they figured out how to engineer it right. They sent that spacecraft to Venus and they descended with this space capsule down to the surface of Venus. And along the way, they sampled Venus's atmospheric gases. And one of the things they sampled for was deuterium. In Venus's atmosphere, the abundance of deuterium is one deuterium atom for every 60 hydrogens. How many times above the cosmic abundance of deuterium is the concentration of deuterium in Venus's atmosphere?
100?
100 times more deuterium. How did that deuterium get there, Ian?
That's a great question.
Oh, I thought the answer might be
If
obvious.
you're just talking about like planetary formation, it was the disk.
I'm not talking about planetary formation. I'm talking about something that happened to Venus over time. Where does water come from in a planet's atmosphere?
So, volcanism?
That's right. But what happens when Venus releases its water?
It vaporizes.
It becomes steam, it breaks up.
What breaks it up?
Solar radiation.
Solar wind. Solar
Yeah.
radiation means light.
Yeah,
It's
yeah, yeah.
solar wind. Sorry, my drawing skills kind of suck here. Okay. Imagine you are a molecule of water that has a deuterium stuck to it. And along comes a high-speed proton from the solar wind. Bam. Venus has no magnetic field. You bust apart the water molecule, and now you have a free hydrogen and you have a free deuterium. Tell me the story of what happens.
The hydrogen is lost and the deuterium remains in the atmosphere.
Because they're on either side of that cutoff for planetary atmospheric loss, the hydrogens are light enough to bounce off into space. The deuteriums get stuck in the atmosphere. And over time, you build up more and more deuterium as this keeps happening. In other words, the Russian scientists used the 60-to-1 ratio of hydrogen to deuterium as evidence as a smoking gun that Venus once contained an Earth's ocean worth of water. And that buildup of deuterium only could have come from one place, busted up water molecules. That's how they proved that Venus one point had water that got lost. So let's write that down in a simple sentence. The answer to part C then is the fact that hydrogen escapes to space while deuterium remains, comma, coupled with the observation of a 60 hydrogen to 1 deuterium abundance in Venus's atmosphere suggests that the solar wind has broken apart an ocean's worth of water molecules on Venus. And that concludes our homework for today. Today's homework was actually pretty crunchy, but we got through it. Took a little longer than I would have liked, but I do allocate 2 hours for homework. I've been managing to clock it in an hour and 30 minutes. Today it took an hour and 40, so be it. Okay. I'm going to try to stop this video to keep it as short as possible. Let me give one last look there in case anyone is still writing. To the people watching the video, we'll see you next Monday. We'll finish atmospheres and move into the Jovian planets. Everyone start thinking about whether you want to take the final or whether you want to double your midterm grade and weasel out of taking a final exam. Okay? I'll see the rest of you on Monday.